Today we're going to learn about subatomic particles. What is an atom? Atoms are the smallest part of matter that has all of the characteristic properties of matter. In particular, atoms correspond to elements. The smallest particle for a compound would be a molecule. Same idea of it being the smallest particle, however, molecules are a collection of atoms that are bound together. Atoms are exceptionally tiny. We haven't quite been able to capture any visual evidence or pictures of them just yet. However, electron microscopes have come exceptionally close in the very recent years, and so you can expect that perhaps in your lifetime you might actually be able to see an atom. Why are they so hard to see? Atoms are approximately 10 to the negative 10th meters in size. They are exceptionally tiny. The size, 10 to the negative 10th meters, is also called an angstrom. There are things that are smaller than the atom, however. Atoms are made of subatomic particles. These are the various particles that are found inside the atom that make each atom for each element unique. And so there will be varying numbers of each subatomic particle inside different atoms. There are many different subatomic particles. In fact, all the subatomic particles are then made up of even smaller particles. But the three we're going to talk about today are protons, neutrons, and electrons. Protons are positively charged, have a mass of 1.67 times 10 to the negative 27th kilograms, which is very, very tiny, which you might expect because of how small they are in length. And they are located inside the nucleus of an atom. The nucleus of the atom is the central part of it, much in the way that the nucleus of a cell is the central operating area for a cell. Electrons are negatively charged. They have a mass of 9.11 times 10 to the negative 34th kilograms, which you'll notice is even smaller than a proton by quite a significant amount. They are located outside of the nucleus in what we're going to call for now the orbital cloud. Basically, there are locations outside the nucleus where the electrons are housed. We will talk about where the electrons are usually found in a later unit. Neutrons are neutrally charged, have a mass of 1.67 times 10 to the negative 27 kilograms, which is the same as the protons. It's only some decimal places that are not listed here where they differ. They are also located inside the nucleus. In fact, they help to hold the nucleus together because the protons would normally try to repel each other, so they need another particle in there to help stabilize the nucleus. So, how do we determine how many of the subatomic particles are present in a given atom? The number of protons in an atom corresponds to its atomic number on the periodic table. So for example, gold is atomic number 79, and therefore an atom of gold will always have 79 protons in it. Let's deal with electrons now, the other charged particle. Atoms are neutral overall, which means the number of protons and electrons must be the same for an atom. So, since there are 79 protons in an atom of gold, and protons are positive, there must be 79 of our negatively charged particle, the electron, as well. Please note, this is only true for atoms. Ions will not have a balanced number, and we will deal with them in a later set of notes. Neutrons are a little bit trickier. A couple of things we need to discuss first. As we mentioned earlier, electrons are exceptionally tiny compared to protons and neutrons. They have approximately 1/1000th the mass of these other two. Therefore, when we consider the mass of an atom, the vast majority of it comes from the protons and neutrons, and therefore when we're talking about the mass, we generally ignore the contribution from electrons. The mass of an atom is represented in a unit other than kilograms, called the atomic mass unit, or AMU for short. This is done so that the numbers are more manageable. 1 AMU is equal to 1.66 times 10 to the negative 27 kilograms. You'll notice this is exceptionally close to the mass of protons and neutrons, and so for the sake of our rounding, we are going to say that 1 AMU would be the equivalent in mass of a proton or a neutron. An important thing to note is there is a mass on the periodic table for the square of an element. However, that is an average atomic mass. It is a weighted average of all the possible masses that an atom could have, because not all atoms of a particular element are quite identical. We will talk more about isotopes and atomic mass in a later unit. So usually, for the individual atom or isotope that we are dealing with, we will have to specify its mass when we say its name. For example, gold-197 is an atom of gold that has a mass of 197 AMUs. This means, with what we've already discussed, that the 197 AMUs comes from the number of protons and neutrons in the atom. So the total from both of them added together will equal 197. Since we already know that there are 79 protons, that means the remaining mass must come from the neutrons. So therefore, there must be 118 neutrons in an atom of gold-197. So to summarize what we have just discussed, the number of protons is equal to the atomic number. In order to maintain neutrality, the number of electrons for an atom must equal the number of protons. And the atomic mass for an individual atom or isotope is equal to the protons plus the neutrons. This means if you wish to find neutrons, simply subtract the number of protons from the mass. Note, for this, please make sure you are using the individual isotope's mass and not the average mass located on the periodic table. So let's look at an example. Germanium-74 is the most abundant isotope of germanium. Let's determine the number of subatomic particles present in an atom of germanium-74. You'll see here on the right side of the screen a square of the periodic table that corresponds to germanium. Germanium is atomic number 32, which means germanium has 32 protons. So now that we know it has 32 protons, we also know it has 32 of what? In order to remain neutral, it must also have 32 electrons. The final thing we must determine is the number of neutrons. Again, this one is the most tricky. We have to look at the mass, which is 74, and subtract the number of protons. Therefore, since 72 minus 32 equals 42, there must be 42 neutrons in an atom of germanium-74. A quick note about written expression for elements. When we give the name of an individual isotope, it is generally written as element, hyphen, and then the number for the mass. Examples of this might be carbon-12, phosphorus-32, uranium-238. When you write the symbol for it, you'll notice here on the right there is an example of the symbol that includes both the atomic mass and atomic number. You have the symbol in the center. In this case, we're dealing with carbon, so it's a C. Superscripted in the top left corner is the mass. This is carbon-12. Subscripted in the bottom left corner is the atomic number. This is optional, since with the symbol I should be able to take a guess what the atomic number is, because each atomic number is unique for each element, as is their symbol.